Okay, continuing on the fourth part of lecture 5, um, I just want to briefly um, come back to interfaces, especially in metal matrix composites, because these have a huge impact on the final properties of the composite material. This can affect the bonding between the matrix and the fibers. It can create crystallographic differences similar to what you will find in an alloy. There could be changes in modulus, there could be um, changes in chemical potential, and there could definitely be changes in the coefficient of thermal expansion between the matrix and the fibers. For example, if you have an uh, nickel aluminum eutectic with chromium fibers, um, there could be a network of interfacial dislocations, and that can cause a tremendous transition in properties between the matrix and the fibers. And this could benefit the composite properties, or it could also work against that. So if you use it properly, you can use it to your advantage. There could be mechanical bonding between the matrix and the fibers in, say, alumina type of a composite material. So if you have, um, for example, if you had uh, cracks between the matrix and the fibers, that can result in a different stress strain behavior of the composite material itself. Um, if you had steep sided pits, so you can see that it shows much higher strength, crack linear density, and it can show much higher failure to strain compared to the other types of composite materials. So you can actually calculate the radial stress at the interface based on the elastic modulus of the matrix and the fibers and other constituent properties of the composite material itself. So this is a simple formula. It's very similar to the composite properties itself. If you had, say, alumina fibers in a magnesium alloy matrix, there could be a reaction zone around it that can result in twins in the magnesium matrix, which can result in plastic deformation of the magnesium due to the thermal stresses. If you're doing, say, the applications such as a ballistic impact type of application where you are using carbon fiber reinforcement in alumina, although you have to be very, very careful with this process because the carbon itself can result in a galvanic potential difference between the aluminum and the carbon itself. So it can initiate corrosion from those points. Or, for example, sometimes what will happen is that the carbon itself will get reacted with the aluminum when it is poured into the mold, and it can result in aluminum carbide, subscript 3, ALC3 aluminum carbide, which actually is strong at room temperature, but over a period of time it starts becoming a powdery material. And so you will have a block of material that is very stable as soon as you make it, but over a period of time, say for example 6 months or a year or whatever, the whole block will just fall off into powder, which is not a good thing. So you got to protect the carbon fibers before you infiltrate that with the aluminum metal. So this can also be the case in the case of boron fibers in a titanium composite. You have to coat them. If you um, if you don't coat that, the metal will react and impregnate into the fibers itself, which will result in a reduction in properties. But if you coat it with, say, silicon carbide or with boron carbide, it can protect, and the amount of the distance that um, gets reacted with the metal itself is much lower in this case. So you can see that at a much higher schematic, a schematic that is at a much larger um, magnification, you can see that you have carbon fibers or silicon carbide fibers. You take a carbon fiber and put silicon carbide coating on top of that, and then you put yet another coating of a secondary carbon layer, and then you put a final layer of titanium carbide. And this is such that it the fiber does not react with the matrix, which is the Ti64 type of alloy. So by doing that, you can still get much higher properties. But the difficulty with this kind of an approach is that this fiber could be as much as about 200 to 300 microns in diameter, which means that the effectiveness of reinforcement is not as pronounced as if it were to be with a 5 to 10 micron type of a composite. 5 to 10 micron type of a carbon fiber. So what happens is that if you have these fibers, it can cause some kind of an edge pit effect around and dislocations around the fiber itself. So this is in the case of tungsten fiber in a copper matrix. So you are creating dislocations around the fibers itself, and that can result in a different kind of a property for the composite material. So these types of defects around the fibers are going to affect your final properties. Okay, now you can see that say for example, if you had silicon carbide whiskers in an aluminum matrix, and the application is for making wear resistant aluminum pistons, which is used for it used to be used for the the Honda sports cars, but I think it is being used for many of the newer cars more recently. So you can see that when you blend the two together, the aluminum can form aluminum carbide, and that aluminum carbide can become brittle and powdery over a period of time. So you have to prevent that reaction by using high levels of silicon in the matrix. So about 10% silicon. So that will prevent that reaction and form extremely good composite material with excellent wear properties. So in this case, the recommendation is that use only high silicon aluminum alloys as a matrix for making composites by casting out with silicon carbide particles as a reinforcement. So you might be using aluminum 11% silicon for making the metal mix composite. Again, another example of different metal matrix composite systems. Okay, so when you make the composite, this is the schematic of that. You can see that the fibers are not oriented in any one particular direction, but when you extrude that, you can get extremely good particle orientation in the direction of the extrusion itself, which will give you directional properties for the composite material. So this is the TEM image of the composite material. You can see the different fiber um, orientations depending upon the material itself. So you can see the interface itself. And I want to avoid the reaction between the matrix and the fibers so that the fibers are not degraded in mechanical properties. So this is another dark field image of the TM interface of the silicon carbide viscose reinforced aluminum. Okay. So now let me come to a slightly different form of composite fabrication. Now there are many different groups that make composites by different methods, and this was one of the methods that I had a part in developing about 10-12 years ago, and we called it co-injection resin transfer molding for a hybrid type of a composite material. This process was originally developed at University of Delaware Center for Composite Materials for polymer matrix composite. So they wanted to make fire resistant composite, so you had um, a phenolic layer on top of a epoxy matrix. So the phenolic reduced improved the fire retardancy of the composite and gave it excellent fire retardancy for the composite material itself. So this is a single mold vacuum bag procedure that injects multiple resin systems into a fiber layer. There is an intermediate layer of polysulfone that will bond the two parts together, two matrix areas together, and it's an environmentally friendly process, and it reduces the processing waste. So you are making a multifunctional type of a material using this kind of a process. So this is a schematic of the process itself. So you have a phenolic preform and a vinyl ester preform. So this is a composite material that is used by the Navy for especially for ship board or board structures, board type of structures. Um, so you want the composite material not to catch fire. So by doing that, you are improving the properties, especially for the fire retardancy is concerned. In our case, what we used it for was for making integrally co-cured polymer matrix composite, ceramic matrix composite structure. So you have a graphite epoxy shell and you have a novel heat shield based on gel casting ceramic material. And we use that for injecting two types of materials. One would be the epoxy itself and the other one would be a ceramic. Like, it can be the ceramic, can be silicon nitride, silicon carbide, silons or zirconium carbide that can withstand very high temperatures. So the inside would still have the right type of mechanical properties, but the outside would have the high temperature properties that you are requiring. and after debinding, these formulations can withstand up to 1000 degrees centigrade. So you inject that, and I won't go over too much of the details here, but the main advantage is that these um, ceramic slurries have got viscosities that are very similar to epoxies or wine esters and things like that, and it allows us to infiltrate that into the fiber preform itself. So if you make a plate, you can see the cross section here. You make a ceramic layer and you have an epoxy layer, and it is very well bonded between the two because of the polysulfone layer between. So here in this case we use that for demonstrating a huge missile casing. So the advantage is that the epoxy matrix would still provide the mechanical properties, but the outside layer would still retain its properties because, I mean, especially if you are having, say, for example, a missile casing for a hypersonic application. Um, so when it is coming back into the Earth's atmosphere, that outside layer is going to get extremely hot. But because of the ceramic layer on top, it can still withstand the temperatures and still maintain the mechanical properties required for the missile casing. So we checked the ceramic heat shield properties, and what it showed us was that the mechanical properties uh, and the ceramic properties remained constant, and we were able to get the right kind of properties. For example, what we did was to, I mean, so this is the full scale component. This is about 12 feet long by about 6 inches in diameter. So the outside ceramic layer is only about 0.1 to 0.2 inches in thickness, and the inside layer is again about 0.4 inches in thickness. We tested that in an aero heat type of a structure. So we put the tube inside this and we heated the outside up to say 1000 degrees centigrade or whatever. And the first time we did that, the inner tube reached only 550 degrees Fahrenheit. So we stopped the test and then we repeated the test a second time. And even after the second test, the tube was still structurally sound. What we found was that we had to reduce the thermal conductivity of the ceramic itself in order that we got the best performance from the missile casing. So what we did was we added some kind of um, ceramic microballoons to the ceramic slurry, and we were able to infiltrate that and get the lower properties, a lower thermal conductivity that we required for this. So that's the last part of lecture 5. So I will start with lecture 6 in the next section.